Hello everyone. So, in last class we discussed about the simple algorithm and also we have derived the pressure correction equation from the continuity equation. Simple algorithm has been widely used in the literature, but there are number of attempts to accelerate the convergence. So, today we will discuss two such algorithms, one is simpler and another is simplex. So, there is a drawback of simple algorithm. So, dropping the summation of a n b u prime n b slows down the convergence. So, today we will discuss how to accelerate this simple algorithm. So, first we will discuss about the simpler algorithm. So, what is simpler? It is simple revised. So, semi implicit method for pressure linked equation revised. Simple R. Okay. So, this is your simple semi implicit method for pressure linked equation and R for revised. So, this is your simpler algorithm. So, you have seen that in simple algorithm first we need to gauge the pressure field, and if you have a good pressure field obviously the simple algorithm will converge faster. In simpler algorithm we calculate the pressure from the known velocity field. Now, let us write the discretized momentum equation for u e and v n. Okay. So, for u e you can see at this main control volume for velocity u e we are writing the discretized equation a e u e is equal to summation of a n b u n b, okay, for all the neighbors plus the source term for u at point E and the pressure gradient term. What is the pressure gradient term? So, you can see, so in the for u velocity, so the pressure gradient is P E minus P P into delta y. So, minus delta y into P E minus P P, okay. And A n V n is equal to, so for the V momentum equation you can see here we are solving for V n. So, discretized equation you can write for this control volume as summation of n b V n b plus B source term for V at point n minus, so what is the area delta x and the gradient is P n minus P n minus P p. Okay. So, now let us write the velocities dividing the diagonal term. So, you can write u e as summation of a n b u n b plus b u e divided by a e, okay, and minus we will write this as d e p e minus p p, okay, where d e is your delta y by a e, okay, delta y by a e. Similarly, for V n you can write V n is equal to summation of a n b V n b plus V V n divided by a n minus d n p n minus p p, where d n is your delta x divided by the diagonal coefficient a n. Okay. So, this term, okay, will represent as u e hat, okay, and this term will represent as v n hat. So, if you represent like this, then you will, then we can write u e is equal to u e hat minus d e p e minus p p and v n is equal to v n hat minus d n p n minus p p. Okay. So, similarly you can write for the UW and VS. So, UW you can write UW hat minus DW into P. So, for the waste phase you can see the pressure gradient is PP minus PW. So, it is PP minus PW, and for VS you can write, and the pressure gradient for this south phase VS you can write PP minus PS, and dW is your delta y by AW, and ds is your delta x divided by AS. Okay. So, now let us write the discretized continuity equation. So, integrating the continuity equation over this main control volume P. Okay. In last class we have written the equation as Fe minus Fw plus Fn minus Fs is equal to 0. So, this is your discretized continuity equation. Okay. So, now if you put this mass flow rate Fe is equal to rho e ue ae, then what you can write? So, Fe you can write as, so Fe will be okay, rho e ue, and what is ae? Ae is delta y, okay, ae is delta y. So, you can write this as, so now ue you just substitute ue as ue hat minus de pe minus pp. So, if you write that, then you can write rho e ue hat delta y, okay, minus rho e. So, now this is the term. So, it is de, you have delta y into p minus pp. Okay. So, now you can see this rho e ue hat delta y, we can write it as Fe hat minus rho e de delta y pe minus pp. Now, similarly you just write Fw, Fn and Fs. So, Fw will be rho w uw delta y, and uw is this one. So, it will be rho w uw hat delta y minus rho w dw delta y pp minus pw, and this if you represent with Fe hat w, then it will be rho w dw delta y pp minus pw. Similarly, you write Fn is equal to rho n Vn delta x. Okay. So, Vn, so Vn is this one. So, you can write rho n Vn hat delta x minus rho n dn delta x into Pn minus Pp, and this will represent as Fn hat. So, it will be rho n dn delta x Pn minus Pp, and Fs is equal to rho s Vs delta x is equal to rho s. So, this one, sorry, this is your V. So, it will be Vs hat delta x minus rho s ds delta x Pp minus Ps is equal to F s hat minus rho s ds delta x into Pp minus Ps. So, now we will substitute in the discretized continuity equation. Okay. So, if you substitute, what you will get? So, we have Fe minus Fw plus Fn minus Fs is equal to 0. Okay. And now you substitute all these 4 and write Fe plus Fw plus Fn plus Fs. So, it will be, so now first you write Fe minus Fw plus Fn minus Fs. Okay. So, if you write it, so you will get Fe hat minus Fw hat plus Fn hat minus Fs hat. Okay. And rest we have minus rho dE delta y Pe minus Pp. Okay. For Fw, so it is minus Fw, so minus minus plus, so rho w dw delta y Pp minus Pw. Okay. Then for Fn you will get minus rho n dn delta x Pn minus Pp and plus rho s ds delta y P minus Ps. Okay, is equal to 0. So, this is your delta x equal to 0. Okay. So, now you see we are deriving the pressure equation from the known velocity field. So, now you can write in terms of Ap phi p is equal to summation of Nb Pp Nb. So, you can write Ap Pp is equal to summation of Anb Pnb plus B in this form. So, all the pressure Pp you take in the left hand side and all other terms you take in the right hand side. So, if you do that, you can see we have this Pp, Pp, Pp and Pp. So, these coefficients you take in the left hand side. So, if you write it, so it is minus minus plus, so it will be rho e dE delta y, then this plus rho w dw delta y minus minus plus, so it will be rho n dn delta x and this is your plus rho s ds delta x. Okay. So, this is the coefficient of Pp and now you take these terms in the right hand side. Okay. So, what you will write? So, it will be, if you take in the right hand side, it will be positive rho e dE delta y Pe, okay, plus rho w dw delta y Pw plus rho n dn delta y delta x Pn and we have rho s ds delta x Ps and these terms you take in the right hand side. So, you can write minus Fe hat minus Fw hat plus Fn hat minus Fs hat. Okay. So, now this you can write as Ap Pp is equal to Ae Pe plus Aw Pw plus An Pn plus As Ps plus B, okay, or Ap Pp is equal to summation of Anb Pnb plus B, where Ap is equal to Ae plus Aw plus An plus As. You can see the coefficient Ae, this is your Ae, Aw, this is your An, this is your N and this is your As and this is your S. So, Ap is equal to summation of all the neighbor and B is equal to minus Fe hat minus Fw hat plus Fn hat minus Fs hat, okay. And we have Ae as rho e dE delta y, Aw as rho w dw delta y, An is equal to rho n dn delta x and as is equal to rho s ds delta x. Okay. So, in the simpler algorithm from the known velocity field, first we derive this pressure equation. So, first you solve this pressure equation. In simple algorithm which you are actually first guessing the pressure field, instead of that you solve this equation and get a better pressure field, so that it converges faster. So, you can see whatever we have written, it actually does not represent the mass balance, okay, because A p hat is your rho e u e hat. So, it will not actually satisfy the continuity equation. So, it does not represent the mass balance. And you have seen that up to this we have not made any approximation while deriving the pressure equation. So, this pressure with the appropriate boundary condition, this pressure equation with appropriate boundary condition you need to solve to get a pressure field, and using this pressure field now you follow the simple algorithm. Okay. So, then all the rest algorithm will be similar to that simple algorithm, except you do not correct the pressure. Okay. When you will solve the pressure correction equation in the simple algorithm, so here when you are using simpler algorithm you do not correct the pressure, because already you are solving the pressure equation, okay, but you need to correct the velocity field. So, now we will write the simpler algorithm. So, simpler algorithm like this. Okay. So, first is guess the velocity field. Okay. Once you guess the velocity field, you can calculate the ff hat. So, f e hat, f w hat, f n hat, f s hat you can calculate. Then you solve for the pressure equation. Okay. So, if the velocity field is exact, the correct pressure field will be recovered. Okay. So, towards the convergence, when you have the velocity field, correct velocity field, anyway you will get a correct pressure field. Then now you follow the simple algorithm. Okay. So, now we have solved u star v star. Okay. So, this is now guess pressure field. Okay. So, what you have solved the pressure equation, that you will use in this equation to solve u star v star. Okay. Then calculate f f star, okay, and then solve for the pressure correction equation. Pressure correction equation. Okay. So, whatever we derived in the simple algorithm, that you solve. Okay. Then correct velocity only. Okay. So, now you know u star, okay, and you have solved the p prime. So, from p prime you can calculate the u prime. Okay. So, there is a relation, and v is equal to v star plus v prime. Do not correct pressure, okay, because in this step, at third step you have already solved for the correct pressure field with the known velocity field. Okay. So, here you do not correct pressure. So, this is the difference with the simple algorithm. Then check for convergence. Okay. So, if converged, stop, okay, else go to step 2. Okay. So, you go to step 2, okay, with the new velocity whatever you have got it. Okay. With this you calculate this F f star and solve for the pressure equation. So, whatever velocity now you are getting, so that will be used to solve this pressure equation. So, you can see that in simpler algorithm, although there you need to solve one additional equation for pressure, but overall it will take less time to converge as you are giving a correct pressure field. Okay. In the simple algorithm, if you use a correct guessed pressure field, then obviously you will get faster result, but it is very difficult to get a good guessed pressure field. But here you are solving for the pressure with the known velocity field. So, obviously it will converge faster than the simple algorithm, but you need to solve one additional equation for the pressure. Next we will discuss another algorithm, that is Simplec, okay, simple corrected, simple C. So, this is your corrected. So, in this algorithm it is similar to simple algorithm, except without dropping the term we will just use summation of n b u prime n b is equal to u prime b u prime p summation of n b. So, with the main cell value of u prime we will use the main cell value of u prime at cell center small e we will use instead of dropping the full terms. So, that is the difference with simple algorithm. So, if you see, so we have the corrected momentum equation we have derived in the simple algorithm like this. Okay. If you see that we have written first the momentum equation, then we have guessed the pressure field, then we have written A u star, and subtracting the second one from the first we got this corrected momentum equation. So, that is A e u e prime is equal to summation of n b u prime n b minus delta y p prime minus p p prime, and A n v n prime is equal to summation of n b v prime n b, okay, minus delta x into p n prime minus p p prime. So, if you see in the simple algorithm what we did, we dropped these two terms. Okay. So, we dropped these terms, but now we will use some simplification here. So, instead of ignoring this completely, Simplec algorithm attempts to approximate the neighbor correction using cell correction as. So, we will use summation of n b u prime n b, we will write as u prime e summation of n b. Okay. So, now you can see. So, this actually it has to be summation of all these n b u prime n b. So, neighbor values, but neighbor corrections. So, that we are approximating as the cell correction u e prime. Similarly, summation of n b v prime n b we will write it as V n prime summation of n b. Okay. So, V n prime obviously you can see. So, this is your correction at the cell, okay, of this V control volume. So, now from this equation, now if you write it, then what you can write? A e u e prime. So, this now we are approximating as this. So, it will be u e prime summation of a n b minus delta y p e prime minus p p prime. Similarly, a n v n prime you can write. So, this we are now approximating as this. So, v n prime summation of a n b minus delta x p n prime minus p p prime. Okay. So, now if you take in left hand side, so what you can write? A e minus summation of a n b. Okay. So, now you can take common this u e prime. So, u e prime is equal to minus delta y p e prime minus p p prime, and now this you can write as u e prime is equal to minus delta y divided by a e minus summation of a n b p e prime minus p p prime, and this will denote as d. Okay. So, it will be minus d e minus d e into p e prime minus p p prime. Similarly, for this equation you can write a n minus summation of a n b v prime n is equal to minus delta x p n prime minus p p prime. So, that will give you v n prime is equal to minus delta x divided by a n minus summation of a n b p n prime minus p p prime, and this will denote as minus d w minus d n into p n prime minus p p prime. Okay. So, this we have represented as d e and this we have represented as d n. Okay. So, now you can see that we have approximated this neighbor correction value, okay, which we dropped in the simple algorithm. So, that is the difference with the simple algorithm. So, in the simplex algorithm, now we follow the same procedure as simple, except calculating this term d e and d n. Now, let us write the simplex algorithm. Simplex algorithm. So, first, now similar to simple algorithm, gauge the pressure, okay, gauge the pressure field, P star. Okay. Once you gauge the pressure field, solve for U star and V star. Okay. So, once you solve for U star V star, you can calculate F f star. Once you know the F f star, you can solve for the pressure correction equation. Pressure correction equation. P prime. Okay. Now, you correct the pressure and the velocities, but do not under relax it, okay, the pressure, correct the pressure and velocities. So, you correct u as u star plus u prime, v is equal to v star plus v prime, and p is equal to p star plus p prime. Okay. Now, check for convergence. So, if converge top, if converged stop, else go to step 1. Okay. So, with the now this pressure you can take as the gauge pressure field. Okay. So, the simplex algorithm is actually shown as faster than the simple algorithm, because you are not fully dropping this summation of a n b u prime n b, but also here you do not need to solve additional equation as you do in the simpler algorithm. So, now we will discuss about the boundary conditions while solving these discretized equations. Mostly you know the velocity boundary conditions, again we will discuss, but we have derived the pressure correction equation. So, we need to know the boundary conditions for this pressure correction P prime. So, if you consider boundary in the left side, let us say this is your cell. Okay. So, this is your main control volume P, where you are solving small p, and here you are solving u e, here you solving v n, okay, and this is your boundary. Okay. So, this is your small e, this is your small n, this is your small s, and the worst phase is now boundary. Okay. For this particular case, let us write the boundary conditions. So, generally two boundary conditions we will discuss. One is normal velocity is given or the pressure is given. Okay. So, two common boundary conditions are considered. One is your given normal velocity, another is given pressure field. Okay. So, you can see that if velocity is known at the boundary, then you can represent for the fluid flow problem inflow, okay, where velocity will be specified at the inlet, outflow where velocity may be specified at the outlet, and the no slip walls where you have velocities are considered to be 0. So, at a given velocity boundary, we are given the velocity vector u prime b. So, at this boundary, okay, u b is specified. Okay. Okay. So, now if it is inflow, then velocity will be provided. If it is outflow, if you know the outflow boundary condition, then also you can use the velocity is specified, or we can use some outflow boundary condition, and if it is a wall, then there will be no penetration through the boundary and velocities will be 0. So, this type of boundary could involve inflow or outflow boundaries or boundaries normal to which there is no flow. Such as a wall. Okay. So, if you see, let us consider a channel. Okay. So, let us consider flow between two parallel plates. So, third direction is infinite and we are considering flow between two parallel plates. So, you can see that if you want to give the velocity boundary condition, then on the walls there will be no slip. So, velocities will be 0. At the inlet you can specify the velocity boundary condition, you can specify as a uniform velocity boundary condition or some time varying or spatially varying boundary condition. So, at this boundary, okay, you can specify either uniform velocity boundary condition. Okay. So, you can see, let us say u average you are giving, okay, or you can specify a parabolic boundary condition also where u is function of y. Okay. So, if it is x and this is your y, then u is function of x and y. So, this is your inlet. Similarly, at the outlet, okay, you can generally specify the normal direction velocity gradient is 0, del u by del x is equal to 0 and del v by del x is equal to 0. Okay. So, it is a kind of fully developed condition. Okay. So, no axial change of velocities in this direction, and these are the no slip condition. So, wall, so no slip condition. So, you can put u is equal to v is equal to 0 and u is equal to v is equal to 0. If you are specifying normal velocity, then here u is equal to u average and v is equal to 0. So, this in detail we have discussed already in earlier modules. So, now let us discuss about the pressure correction boundary condition. So, if you see the pressure correction equation is A P P P prime is equal to summation of N B P N B prime plus B, okay, where B is equal to minus F star minus F W star plus F n star minus F star. Okay. So, for pressure correction equation, okay, if you write the continuity equation in general, so it is F E minus F W plus F n minus F s is equal to 0, and that substituting the star quantities and the prime quantities, we have derived this pressure correction equation. Okay. So, for this boundary, let us say again, let us consider this left boundary. So, this is your capital P, this is your small e, small n, small s, and this is your west face, which is your boundary. Okay. So, for east face, if you write the F e prime, then it will be rho e minus rho e d e a e is delta y and F e star is your rho e e star into delta y. So, F e we have written as F e star plus F e prime. Now, you see, if velocity is specified at the boundary, okay, then mass flow rate is known. So, you do not need any correction in the mass flow rate. Okay. So, you can see this is your F is equal to F star plus F e prime, and if velocity is known, then this is your correct velocity. Okay. So, that means you do not need any correction F e prime. So, F e prime will be 0. So, So, you can see that your mass flow rate we have written in terms of the start quantities plus the correction quantity. Now, for this boundary if you write, then F b prime is equal to, you can write rho b dB delta y, okay, P p prime. So, this is not be delta y, so yes, delta y P p prime minus P b prime. Okay. So, now you can see that if velocity is known, then A p is equal to A b is equal to F b star plus F b prime. So, at the boundary if velocity is known, then the mass flux is known. If mass flow rate is known, so if velocity is known, the mass flow rate is known. If mass flow rate is known, you do not need any correction at the boundary. So, that means in this case your F b prime will be 0, okay, because you do not need any correction, because you have the velocity field is specified. Okay. Velocity is known at the boundary. Okay. So, F b prime, so you do not need actually any boundary condition for the pressure correction, because this term you will not add while adding in this equation. Okay. So, whatever this F w which is actually coming as F b, so F b will be just in terms of velocities, not in terms of the pressure correction. So, you do not need any boundary condition for pressure correction for the known velocity. And in other words, also you can say that if it is 0, if F b prime is 0, okay, then this will be 0, that means it will be P p prime minus P b prime will be 0, and hence you can write this as the P b prime is equal to P p prime. That means at this point you are applying the kind of Neumann boundary condition P p prime by delta x is equal to 0. Okay. So, this is x direction, this is your y direction. So, obviously del p prime by del x is 0. However, these pressure correction values are not required for the boundary, because you will not add it in the pressure correction equation while solving it. Okay. And if pressure is specified at the boundary, what will happen? So, in general, when you have a flow inside a channel, at the outlet we specify the pressure which is maybe the atmospheric pressure open to the atmosphere. So, the you can say it as the atmospheric pressure at the outlet. So, if it is so, then you do not need any correction at the boundary, right. So, that means P prime will be 0 at the boundary. So, at a given pressure boundary, the pressure correction P b prime is set equal to 0. That means P b prime will be 0. Okay. So, you can see that if pressure is specified at the boundary, then you do not need any actually correction in the pressure. So, P b prime will be 0, and if velocity is specified, then you know the mass flow rate, and if you know the mass flow rate, you directly put it in the pressure correction equation, so that you do not need any pressure correction boundary condition. That means so for the known velocity at boundary the known flow rate is incorporated directly into the mass balance equation for cell P, okay, so which we have written here. Okay. So, there we directly put the value of FB is equal to rho B U B delta y. Okay. So, this we directly put. So, because FB prime is 0. Okay. So, this we directly put for this FW, okay, which is for this particular case it is FB, and rest we can represent in terms of pressure correction. Okay. So, those are interior points. So, you and if the pressure is specified, then P is P star plus P prime, right. So, PB is PB star plus PP prime. So, if pressure is specified, then PB is known. So, you do not need any pressure correction. In today's class, we discussed two variants of simple algorithm which are known as simpler, simple revised, and simplex, simple corrected. So, these algorithm we have discussed which are actually to accelerate the convergence rate. So, in simpler algorithm we have seen that instead of guessing the pressure field with the known velocity field, we solve for the pressure equation, and that is obviously a good guess pressure field and it converges faster than the simple algorithm. Rest of the algorithm is similar to simple algorithm, except you do not need to correct the pressure because you are solving a pressure equation. So, that is your correct pressure field from the known velocity field. So, you do not correct the pressure in the simpler algorithm. In simplex algorithm, it is also faster than the simple algorithm. Here, without dropping the neighbor correction term, you write it in terms of the correction term of the cell center. Other algorithm is similar to simple algorithm, but as you are not dropping this summation of NB u prime NB, you get faster convergence than the simple algorithm. Finally, we discussed the velocity boundary condition and the pressure correction boundary condition. For pressure correction boundary condition, if velocity is known, so you know the mass flux, so you know the mass flow rate, so you do not need any pressure correction boundary condition. And if pressure is specified at the boundary, then you do not need any pressure correction. So, that means P prime at the boundary is 0. Thank you.